Welcome back. Today I will show you how to implement the Perceptron learning rule based on our example. So basically working from the example to a usable code that could be then applied to any other dataset. So first let me introduce a few libraries again. We import our NumPy and for plotting matplotlib. Then I specify our cases, that is just in line with our example, using arrays. And as you can see, we now have an array with dimension 3 and none. Now that is a standard column vector. Now to build up my data matrix, I need to transpose these arrays into row vectors and then basically stack them up. Before doing that, I specify my output. So that's the actual classification observed using another array. And then I want to create my data matrix first by transposing the column vectors. Now there are several ways of achieving that. What I show you here is a different way of reshaping it. I just call this reshape 1 for the first case. And that actually uses a technique from slicing. So that should reshape my first case into, as you can see, that works into a row vector. And I do this now for all the other cases as well. And finally, I want to add all of it into the data matrix, and I use our vertical stack, so it's the vstack command. Inside the brackets, I pass in a tuple. Tuples are indicated using brackets and, most importantly, a comma. So that should create our data matrix. Let me run this. We see our structure. This is the first case, second, third case. The first column is our bias unit, so that's our constant term. That is our x1 and that would be our x2. So that is looking good. Now I specify initial weights. And as in the example, I simply used all zeros. Dimension is 3. So that should be fine. Then we have a learning rate. That refers to our eta, which we put at 0.5. And then I have our initial prediction, which refers to our net input, which is the weighted inputs, and that can be achieved using matrix multiplication. starting with the data matrix, which has dimension number of cases times m, the number of inputs, times the weights. The weights have dimension m for number of inputs times 1 as a column vector. So I can simply multiply these two using the matrix multiplication command. That should give me our net inputs. Of course, initially, because w is all 0, that will be all 0. And then to implement the Heaviside step function and to obtain my initial prediction y hat, I use the npvar command. So basically it checks my array wherever a condition is met. You get a positive response. If a condition is not met, you get a negative response. My condition here is set is larger or equal to 0. If that is met, I classify as +1. If it's not met, it's -1. So that should give me my initial prediction. And of course, everything is predicted to be 1 by default, because initially my weights are all equal to 0, which means the net input is all equal to 0, which means everything is predicted as +1. Good, now we have our learning rule. So these are the adjustments. And that just follows from our example. The weights are changed, so plus equal to, so there's a change in weights based on our learning rate eta times comparing our actual value out of output to our prediction times the value of our variable. And all the variables are stored now in different rows. So I have to refer to a row and refer to all the variables. I start here with my first case. So I refer here to 0, which is the first position in my y array, and also here to 0, which is the first position in my prediction array. And in the data matrix, I focus on my first row and I take all the columns. So I just put the column in here, which takes all the columns in the second dimension. So when you go to the data matrix, basically what we do is we look at the first row here, check the first case, and then take 1, 1, 2. We move then to the next one and so on. Yeah? So that would be for the first case. The first case is correctly predicted. Yeah? We would not expect any change in weights, which is of course exactly what you see. And then we continue this exercise for the other two cases. So that goes quite quick. We just move in 1 here and finally 2. And we know only in the last case will we see an adjustment in value of the weights. So running this, I now obtain a different weight as in our case before -1, -3, -1. So that is good. That is very useful. Good. Now, of course, as we know, this adjustment, which we discussed here, this adjustment has to continue. So I need to make sure that I don't change these values only once. I have to do it several times. So I have to think about iterations in this case. Yeah, so that is basically where this loop is now coming from. Now, how can I implement that? One way to implement these iterations is to use a while loop. So I can start by doing the following. I have to specify my while loop and have to think about how we implement that best. Good. So how is this going to happen? So I could now modify my code, which I do here, and I track this further below. So these are my predictions here. I just move that here. Just move things a little bit around, and then my learning rule is coming up here. It's all fine. Get rid of that. So actually I could have done this a bit differently. So I have here my learning rule and my prediction. Then I could specify here my iterations. and I refer to this the maximum number of iterations. So it's max iter for iterations. I set this equal to, say, 100. I have an initial value for my index in my loop, which I set equal to 0. And then I specify a while loop and run all of this inside the while loop. So you can just mark these lines and use tab, so it moves it to the next level of indentation. I use a while loop while I is less than max iter for iteration. Note we start here at 0, so this will give me exactly 100 iterations. So I basically, every time I do this, I initially check my net input, I do an initial prediction, and then I adjust the weights. Yeah. After this is done, the adjustments are done, I basically start increasing my I by 1 and go into the next loop. And I could now for each and every iteration also print out, if I want, the value of these weights, just for illustration purpose. And after everything is done, I could put another print function here, and I could use a formatted string if I want, and just say, yeah, final weight W. Let's do that. Good. As always, let's test this, whether it works or not. The initial weights, I move them a little bit further down here, so that would do, and I start running this. And now what we see is we have now an initial adjustment, which is what we have seen before. Then again it's adjusted, and then it's adjusted for the final time, and then actually you see the weights don't change anymore. So you have very rapidly a conversion to a final outcome. Of course the loop would not stop, because it would keep incrementing by 1 until the I is equal to the max iteration number. So that's not yet a perfect way of implementation, but definitely it's useful. I think that is quite useful. Good. Now if you want, we could start visualizing that. So that would be useful in general. So if you want to plot here, we could do that. So first thing we need is our constant term. Just for the purpose of plotting, I just call this the constant. And of course we know the constant term is simply all 1. I use 100 data points, so I need this 100 dimension. I have an x1 axis here, which again refers to the 100 data points using linspace. We used this before, starting from 0 and going up to 10. For instance, we don't necessarily have to go that far, and we have 100 increments here. Then what we need to consider is our set vector, which is our net inputs. So to get the decision boundary, we note the following. We have our weighted net inputs here. So this is actually how that looks like. It goes to number 2, it goes to number 1 here, and 2. So this is how our net inputs look. Our decision boundary means that z is equal to 0. So we basically have this equation, and then we basically have to rearrange that. If we want to plot our x2 against x1 or over x1, we just solve it for x2, which is obviously equal to, and that should be then divided by my weight W2, and then inside brackets I would get minus W0 and then minus W1 times the x1 axis. Yeah, so that should give me a decision boundary. If you don't quite understand at this point, just think about this for some time. If you're still unsure, ask me if that is a little bit too fast. I start plotting. I give the plot the number 1. We have used this command before. Then I plot, in this case, my x1 axis. And I want to plot now a decision boundary. Now we should actually write down our decision boundary here. It would be useful to spell it correctly. And we just, in fact, implement the equation above using our standard indexing. So it's 1 divided by our weight at last position, then times inside the brackets minus weight at the first position, which is my constant, minus weight in the second position, and then we have our x1 axis. So that's basically implementing this equation here. Oops, that's not helpful. Let me just put this out here. Okay, that's good. And we put in our decision boundary. So that should plot our decision boundary. We can also now, of course, plot as well our other values. Here we just go into the data matrix and we refer to all the cases. So this is capital X. So all the cases, so all the rows. We go position 1, which is the x1 axis. And then we just specify the second position, which is the x2 axis. So here we literally plot our cases, and we want to have it plotted as a scatter plot. So here we use a simple little O for plotting. We can specify a color here, and I just use black. Yeah, that should be okay. Let's do it like this and run it and see whether this actually works out. And now we have here our figure. So we have our decision boundary, we have our cases. You see this is the case which should be a -1 case, and these are the +1 cases, and you see separation has actually occurred, which is good news. Yeah, so that is exactly how this should work out. Okay, that looks very, very promising. Okay. Now, what else do we need to consider? The first thing I think I want to really fix is the fact that at the moment we keep running these iterations, whether we actually found a good solution or not. So that is not the best ever way of doing things. So what we could specify in here is we could actually specify whether the errors are 0 or not. So once you stop making any errors, you would stop making any adjustments. So what I do here is I simply ask for errors, and this can be done. In fact, I want to look at all these cases. So I want to sum up all these errors, and an error is either, of course, making a positive, a false positive, or false negative prediction. So the best way to implement that is to take the absolute value of my y vector minus my y hat vector. So for instance, if I predict a 1 and actually it's a -1, this would give -2, because it's an absolute value, would give me 2. If I predict here -1 and actually it is 1, it would give me a +2. Yeah. So no matter what kind of mistake I make, so a wrong 1 or wrong -1, it would always count as an error if I use the absolute value. Then I simply sum over all these cases. Yeah. And that is the implementation here. And for instance, what I could then do is I could say, okay, if now there is no error anymore, so if this error is equal to 0, I should stop. Now, how do I stop in this case? I stop using the break keyword. That simply breaks the while loop. I could also show a message here, and I put in a message like solution found. So if you see this message, it actually breaks, and it only breaks if basically nothing has changed in terms of a weight adjustment. Yeah. So of course I don't have any placeholder here. I should maybe put this here, solution found. I could, for instance, specify now the actual W. Yeah? Or I could say the actual weights is a solution. There are different ways of phrasing this. It doesn't really matter. Okay, so now we already know that early on we should actually break it. Let's see whether this now works. I run this again, and we have the same figure, which is good. And you see also quite quickly, you see now the message solution found, and you get a final solution here, which is good. So it stops this loop, it stops the while loop once we do not adjust anymore. So that is in fact a very good implementation. One more thing to consider. Now this is working, it's good. There are a few shortcomings. So one thing which would be really useful is to generalize this for all types of data matrices. At the moment, of course, this would only work if I have exactly 3 cases because of our implementation on these lines 40 to 42. So that is not really the best ever way of thinking about this. So that is definitely a significant weakness. The other weakness is we at the moment have initial values of 0. Now this is completely arbitrary, but it would be more reasonable to have actually a random starting point. I will first tackle the loop here and see how that could be implemented. The best way to do this implementation is to remember the shape command on our matrix X. So if I put in X, our data matrix, and ask for shape, this will give me the number of rows and the number of columns. So if I refer to shape 0, because that's a tuple I obtain, this should give me the number of rows. Yeah, so and that actually specifies how far I can go in this iteration for different cases. So what I do is I use inside my while loop now a for loop. I call this index, in this case n, and I go in range, and in range means that the last point would be exclusive, so it doesn't go up to 3, it actually goes up to 2, which is exactly what we want because we start from 0. And then inside this loop I would then do my adjustments. Yeah, and actually the adjustments are only the next lines. Yeah. Note that the next line 44 is not done all the time for all the cases, otherwise of course my iterations would go up very, very rapidly. Yeah, because it's iteration over the whole sample. So now I have of course the index n in here, so I can replace my 0, and that should exactly do what has been done on all these lines. Yeah, so we can try this. Let's give it a try first, and you see it works quite nicely. It's a much better code because that would now work for any kind of data matrix. Okay. Now the next thing which would be useful is to think very hard about whether this could be implemented as a function, because then I can just call the function, which would be much, much better than always running the whole script. And that's not the best way of implementation. Okay, so how can I do this? I need to think about iterations, I need to think about actually all of that above, and it would be useful to put in this case our initial values as well, which is not great to specify this as 0. So what I can do instead here is I can do here first a random command. So random, rand for random, this is inside the numpy command. So when I run this, it might give me a slightly different solution because it depends on starting points. It still found a solution, so that is fine. And I use here the seed 3, which means if I repeat this, it will give me the same outcome. Now this is a good way of implementation. Okay, so that is quite a useful starting point. And the seed could be also modified. Now if I define a function, I want to actually move all of that inside the function, and I use the def keyword here, and I call this the Perceptron rule. Now in terms of the things we need to pass in our data matrix X, we need our output matrix Y, we need our iterations, they could be specified, I don't want to hard code that. Iterations are an integer, and we need our eta, our learning rate, which is a float. Yeah, so that should define my function. Okay, so that is useful. I could specify here if I want also a seed, but I don't have to do this, but I could for instance put in here random seed. The 3 in here is the dimension of the vector. Yeah? And I use random seed 1. I could also make this, if you want, part of my arguments. That's perfectly fine, so that you are in control, you can override this. So that looks quite useful. Okay, that looks all good. So that I think is quite a useful implementation. Okay, here we get undefined W. Okay, that's correct, because now we are inside our function, so we have to think about what is actually the outcome here. Remove the print functions here, and what I want to return as a function is I want to return here our W. So this is our actual value. Then I actually call the function. So I call the function at the bottom here, and I call this when W is equal to whatever this function gives me. I have to specify now, of course, how many iterations I want. I say now 100 here, and I put my eta as 0.5, and that should in theory work. Let's give it a shot. Let's try this, and it actually does work. Yeah. The benefit of using a function is I can now easily modify this. I could just, of course, I can change my x, I can change my y. I could, of course, then also change my eta. I can just go down to very low levels, and let's see what that actually does. Yeah, but still, it would find solutions. So that is not a bad outcome. But you might see that, like in this case, that the line is different. Yeah, because now it would take my second line as my decision boundary. Yeah, so the decision boundary will be different depending on my starting values, but also depending on my learning rate. If I take a too low learning rate, I might not be able to find any solution. So that is all for today. So that is an implementation of the Perceptron rule, where I show you how to move from an example to a code that could be applied in principle to any other data set. The implementation you find in many books in machine learning. These implementations are a little bit different. Quite often they specify a Perceptron class. Honestly, in my opinion, this works very well as a function, but that is a matter of taste. Good, I hope you enjoyed. If you have any questions, please let me know. Thank you very much.